Hello, everyone. Welcome to another event at ACE. First of all, thanks a lot for attending the event. Um, I wanted to start with introducing what ACE is. ACE is a community of machine learning practitioners and researchers who have gathered around topics in AI research, engineering, and products. We host free live sessions like this one 3 to 5 times a week and produce premium content in various subject areas. To see more, please visit our website. Also, make sure you subscribe to our YouTube channels to get the latest notifications, which is ML Explained, to get notified about the live sessions and other free content. Today, my name is Omar Nada. I'm the Commander Systems team owner, and I'm welcoming Cody Coleman, who is a PhD student at Stanford University. Um, and Cody's main focus is Cody is supervised by Professor Mattia Zaharia and Peter Bayliss. His research focuses on democratizing machine learning by reducing cost of producing state-of-art models and creating novel abstraction that simplify machine learning development and deployment. He has got his bachelor's and master's in electrical engineering and computer science from MIT. Thanks a lot, Cody, for being with us today, and it's all yours now.
Awesome. Thank you, Omar. So I'm Cody Coleman. Today I'm going to be telling you about my work, Similarity Search for Efficient Active Learning and Searching for Our Concepts. So the problem that we're considering is what happens when you want to identify something new. So as a fun example, we can consider fidget spinners, which were kind of a big internet trend in 2017. Now, you might be able to, it's easy to find kind of a few examples of fidget spinners. You might have that readily available, or any concept that you care about classifying. But it's not usually enough examples or enough data to be able to create kind of a very accurate, robust classifier. Fortunately, it's become incredibly easy or kind of more common to have a tremendous amount of unlabeled or weakly labeled data. So inside of this kind of large amount of unlabeled data, we must have many examples of the thing that we're trying to identify, enough to be able to build an accurate classifier. So in this setting, the problem kind of creating this accurate classifier boils down to finding the relevant examples that we care about that are the most informative for improving our model classifier. And fortunately, there's a lot of work on identifying such examples, things like active learning, which tries to identify the most informative and valuable examples to label to improve model performance. And this happens in recommendation, but it also happens in many other areas and many other kind of real world use cases. So for example, you might be an autonomous vehicle company, and you realize that your car is getting stuck behind delivery trucks. So this might be a model debugging use case. And you realize that the car is getting stuck behind delivery trucks because it doesn't realize that it's a delivery truck. It just thinks that it's like any other car. So now you want to actually go back and refine your classes and be able to create a separate class for delivery trucks so that you can plan appropriately. Well, fortunately, you could have a tremendous amount or a large fleet of vehicles or historical data. So there's definitely plenty of examples that you already have or can capture of delivery trucks. And again, we're in this kind of setting where it becomes, how do we find those relevant examples for this new concept? Or finally, it might be an integrity use case. So at the beginning of the pandemic, it was not acceptable to sell N95 masks. At least here in the United States, it wasn't acceptable to sell N95 masks. So if you're a marketplace owner, it can become critical for you to be able to identify this new object so that you can appropriately take action and take down malicious or bad content. And again, this is another setting where the data is going to be very, very skewed here. You're going to have many normal kind of innocent posts, and there might be only a very small percentage of that actually contains the bad or malicious content that you want to take down. So again, in all of these different settings, whether it be kind of traditional classification or recommendation tasks, model debugging, or integrity, it becomes critical to actually accurately identify these rare concepts. Now, even though active learning, and there's a lot of work in active learning at identifying informative examples, there's a bit of an asterisk here, which I'll get to in a little bit. But first, just as a bit of background, I want to dive into what is active learning. So the goal of active learning is to select the best examples to label to improve model performance. And this is done through an iterative process. We start by taking a small number of labeled examples that we use as an initial kind of seed data set. And then we have a much larger amount of unlabeled data to pull from and to label to improve our model performance. And as part of active learning, we start by training a model, and we perform this iterative process of taking that kind of initial model trained on our initial data, applying it to all of our unlabeled data with some selection strategy to identify the most informative examples kind of out of this, out of the large amount of unlabeled data that we have. And then we repeat this process of training and selecting until we've exhausted our entire labeling budget. And then we train our final model that we're going to use for our prediction task. And then active search is a very related problem to active learning, where it again follows an iterative process, but the goal of active search is to select as many positive examples as possible. So this might be relevant for the integrity use case that I talked about earlier, where you want to take down all kind of listings of some contraband or some problematic material. Now, the problem with many existing active learning and active search approaches is that they're too slow for these large-scale industrial data sets that have millions, billions, or even trillions of examples, because of the fact that these methods they scan over all of the unlabeled data to find the global optimal examples to label. And this can be really, really expensive when we're in the setting of large unlabeled data sets. For example, if you're like a data set with 10 billion images, if we ran ResNet like 50 over all of that, that's going to be about like 40 exaflops of computation. And we're doing this repeatedly as we're selecting, kind of doing this iterative process. And this is at every single step. We're spending a massive amount of time and compute to do this. So in our work, Similarity Search for efficient active learning and searching for concepts, which I abbreviate as SEALs, the key insight is actually, let's not look at all of the unlabeled data. Instead, let's only look at the unlabeled examples that are the closest to our currently labeled examples, and use that as our candidate pool and select additional points to label from that. And then as we select those labeled examples, we expand that and expand our candidate pool with the nearest neighbors of those newly labeled examples. So concretely, the SEALs approach looks something like this. We start in the same way. We start with this initial seed data set, and we train our initial model. But instead of applying our selection strategy over all of the unlabeled data, we instead use similarity search, and basically find the nearest neighbors to each one of our labeled examples. We only consider these kind of nearest neighbors to our unlabeled to our labeled examples as our candidate pool for then selecting additional examples to label. And then we take those newly labeled examples and we expand our candidate pool. And then we just repeat this process as we did previously with the original approach of training and selecting examples until we've exhausted our labeling budget. But now, once we get to the point that we've exhausted our labeling budget, we've actually only looked at a small fraction of the unlabeled data. And because we're doing this k-nearest neighbors expansion, SEALs basically allows existing or active learning and active search procedures to scale with the size of the labeled data rather than the unlabeled data. And we can actually use this value of k to kind of provide some flexibility. Now, if we compare this to our original approach that scanned globally over all of the data, we're only looking at a fraction of the data. But even though we're only looking at this very small fraction of the unlabeled data, we surprisingly empirically find that the final model still achieves the same predictive performance. And kind of part of the reason for this is that as representation learning has gotten much better through either transfer learning or through self-supervised learning, we find that unseen concepts are actually still well clustered in this kind of latent feature embedding space that these representations learn. So we actually don't need to look globally over all the data, relevant examples that we care about are actually kind of tightly clustered in this latent space, allowing us to go with this approach of expanding locally rather than searching globally. So we evaluated this seals approach on a number of different data sets. I'm going to talk about two of those data sets here. The first setup is evaluated on ImageNet, where we simulate this kind of rare classes by taking half of the classes from ImageNet, about 500 classes. We train ResNet 50, and we use that as our feature extractor. And then we treat the remaining 500 classes as unseen concepts, and we train binary classifiers for each concept. So this basically gives us a setting where it's each concept is like 1 in 500 examples. And then we're training, we're collecting binary labels for each class, and we're training a logistic regression model on the extracted features for our final classifier. And we evaluate a bunch of different selection strategies. The dashed gray line that you're going to see in the plots will represent the performance that we got with full supervision using all the labels from ImageNet. We also look at random sampling. And then for an active search selection strategy, we use most likely positive, which basically takes the points that have the highest probability of being positive under the current model. And this is linear. This scales linearly in the size of the unlabeled data. For active learning, we look at max entropy uncertainty sampling, which takes the points with the highest entropy based off of the predicted class probabilities of our current model. And again, this scales linearly with the size of the unlabeled data. And then finally, we look at information density, which selects the points that are in regions of both high uncertainty and high density, where it quantifies the density by comparing the point, its distance to all other points in the unlabeled data set. And as a result, scales quadratically with the size of the unlabeled data. And because active learning and active search are similar in the procedure and just differ in the selection kind of procedure, or the selection metric or strategy, we evaluate kind of all three of these methods, both for active learning and active search. So for active learning, we find that the seals approaches are within 0.001 mean average precision of the baseline equivalence. So you can see that in this plot here, as the similarly colored lines are basically indistinguishable as far as the performance that they achieve with 2,000 labels. This is 2,000 labels out of a total of 600,000 labeled examples, since we're using half of ImageNet. So less than 1% of the overall labels available for any one of these classes. And all of these methods, both seals and active, both seals and the baseline approaches, substantially outperform random sampling. So this actually gives us kind of the best of both worlds in a sense with seals, where we can achieve the performance in mean average precision that we would get from active learning, but we don't have to spend as much time in the computation. And we see this because we can look at the amount of the pool size and how many examples that we have to consider, and it's less than 10%, closer to 7 or 6% for the different selection strategies when we're at that labeling budget of 2,000. And similarly, for recall of positive examples, for the active search case, where we're again trying to get as many positive examples, we're within 0.14% of the recall of the baseline approaches for active search. And again, all while considering less than 10% of the unlabeled data for ImageNet. To take this to an even larger scale, we use the open image data set, which at the time of writing had about 6.8 million images with human labels. And these images are spread across 20,000 different concepts, or there's 20,000 different concepts in these 6.8 million images. We selected images that had less than 7,000 labels in the training set. So this represented somewhere between 0.002% of the data, so about 1 in 50,000. To 0.088%, so about like 1 in 1,000 examples for these classes in the unlabeled data set. And we continue to use ResNet 50, but we pre-trained it on all of the ImageNet models. So you can imagine just like basically standard ResNet training transfer learning setup here. And we collected binary labels and trained logistic regression. Also, we selected classes that did not overlap with ImageNet. So we manually verified that the classes that we selected and evaluated that had less than 7,000 labeled examples did not appear in ImageNet. So again, these are truly unseen concepts. And we find very similar results to the simulated case that we had in ImageNet, where the seals approaches were within 0.013 mean average precision of the baseline equivalence for active learning, and within 0.1% recall for active search, while considering less than 1% of the data. So this represents kind of like 2 orders of magnitude improvement in the selection time for linear methods like most likely positive as well as max entropy. And then for things such as information density, you'll notice that we don't even have the solid line for information density because I let this run for days and it never completed because of the size of the unlabeled data set and the fact that it scales quadratically. Whereas now, if we use seals, it actually finishes in a reasonable amount of time, taking seconds rather than days to complete a round of selection. So just to kind of summarize everything, the key insight or the seals approach is basically rather than searching globally for all of the optimal examples to label, we instead start with nearest neighbors to our labeled examples, and we slowly grow our pool as we continue to select more and more labeled examples. And the result of this is that we still achieve a similar mean average precision and recall to the baseline approaches, while processing orders of magnitude fewer examples and dramatically improving the computational efficiency of active learning and active search methods, allowing them to scale to industrial real-world data sets. And with that, thank you. And I'll open it up to questions.
Okay, so this is very interesting. It's quite not too complicated of an idea, but it's very effective in terms of how much time you can save given the massive data sets. Okay, yeah. So now it's time for questions. If there's any question, please post them on the chat and I'll be able to take them to Cody. Up until then, if there's a question, I'll bring it to you. But for now, I actually have a couple of questions. So my understanding when you do the random sampling, so you have a lot of labeled data set, and you choose the positive cases that you want to identify, right? So in the basically the autonomous driving, for example, is a truck in front of you. Or in the N95 is basically selling N95 masks. My question would be if when you're trying to do the nearest neighbor, the KNN or the nearest neighbor algorithm, are you getting the positive and the negative examples? If the nearest neighbor is a negative example, do you include that in the data set or no?
Yeah, so when we do the k-nearest neighbors expansion in the unlabeled pool, we don't know the label of that example. Mm-hmm. So we have this pool of unlabeled examples that are the nearest neighbors to our labeled examples. And then we take our selection strategies, whether it be most likely positive, max entropy, or whatnot. And basically these rank and they score each one of the points, and then we select the points with the highest score. And then this will either be positive or negative. So we don't know if it's going to be positive or negative. It could be either positive or negative as a resulting label. Generally, these things, and with active learning in particular, because of the fact that you kind of move closer and closer to the margin, you end up with kind of more of a balanced data set. So it's not just purely positive examples. You're also getting kind of hard negative examples that are very close to the decision boundary as well. Also, I want to say that kind of you had a great point about the simplicity of this method is actually quite nice. Even though we only evaluate 3 selection strategies here, you can imagine this can be applied kind of universally and transparently to many different active learning methods.
You're absolutely right. I can see this from, at least from my experience, you can see that very easily in a commender system space, because in a commender system the number of items that you want is very small compared to the whole items on the website, or even in cybersecurity, an attack is very small percentage of the normal transactions that you have. So training on such a thing or using this kind of method to actually train a model, it can massively improve a lot.
Yeah.
So we have a question here saying, how were the initial label 2000 selected? And
Hmm.
was it stratified over candidate classes?
Yeah. So let's see. I think. So the way that the initial 2000 is selected, we selected kind of because of the fact that we're not in the case that we're using kind of like the full vector labels, right? So for like ImageNet, right, you have basically 1,000 labels. Each
Mhm.
example has like 1,000 labels. We're considering like a binary case here. So we select 2,000 examples for each one of the classes, or 2,000 binary labels for each one of the classes, where there is a slight skew between the positive examples and the negative examples in this kind of initial subset. Uh, the rationale for this is that negative examples are extremely cheap to come by in this setting. Like most things are going to be
Mhm.
negative, so you just kind of keep
Mhm.
sampling until you get to your like positive examples. And having a few more negatives helps like kind of explore the space a little bit more.
Sure.
But they're selected kind of randomly from the overall pool of unlabeled examples.
Okay, so my understanding is, if you, let's say in your data set, if you have five classes, you select 2000 for each class. You select 2000 positive and 2000 negative for each specific class. So you end up with 10,000, actually 20,000 samples, right? So
Yes.
2000 on each. Okay, okay,
Yeah.
and that is random selection. It's not static. Well, it's not random anymore, I guess. It's random per class, I guess. We
Yeah.
can
Yeah.
put it that way.
Yeah.
Okay.
Totally.
Okay.
So yeah, to clarify that also as well, like in the paper, we actually break down in a table what's the performance for each individual class.
Mm-hmm.
Um, like if you were to do the setup and you just focus on a specific class. Here, since we're like kind of simulating this in the case of like the ImageNet example, we aggregate over all of the classes to create this like kind of plot to show how does it improve for a variety of classes rather than just for like one specific class.
Okay. There's another question that is not a bit related to the paper, but it's saying basically that the person missed the presentation. If they have questions for you, would you be okay if they can email you and any offline questions?
Oh, yeah, sure, yeah.
Okay, so yeah, your email is on the paper, so if they have any question, they can always email you. Okay, I
Yeah,
have another question. So, in this specific slide, so you have the MLP, max entropy, and the information density.
yeah.
Um, of course, MLP is the kind of fast compared to information density, but um, if you have to choose one algorithm to go with, which one would it be, given the running time and the accuracy?
Mm. Yeah, so I would say actually like maximum entropy is maybe like the most popular, or like uncertainty sampling in general is maybe the most popular kind of method for active learning in general.
Hmm.
Um, but there is a lot of variety depending on your specific use case of like what does uncertainty mean, and also dealing with kind of other issues. Maybe it's like diversity and things like that. If you're like kind of selecting larger batches or you want to assume some coverage
Hmm.
of
Hmm.
the data. So it depends a little bit on your domain, but by and large, the most kind of popular, most common active learning strategy is uncertainty sampling, here represented by maximum entropy uncertainty sampling, which is actually equivalent to like least confidence or max margin in this like binary classification case.
Awesome. Yeah, it's even in the command system, it's very things. Okay. Um, for people to maybe understand it more, so your idea or your model is basically not innovation in the modeling piece, but even actually in the pre-modeling, where you keep on selecting, iteratively selecting samples that will just go to the model to make the model much faster and with the same accuracy.
Yeah.
Does it matter what is the model itself eventually, or no?
So we kind of take the model as an abstraction here. You can use many different models, for example. In this case, we do kind of like this pre-trained frozen kind of embeddings and then train a logistic regression model on it for simplicity and kind of a standard case, especially as we see kind of more common things like self-supervised learning and things like that, where you have like a shared trunk across many things. Prior work that I did around active learning show that you can actually use like a heterogeneous or like selection by proxy, where you can use maybe the simple logistic regression classifier to select points and then ultimately create a data set for like some other model, as far as like maybe you want to do a deep model or something else or some kind of other computationally expensive model that you train on the final data set. But and that this transfers like fairly kind of across these different things. But really also similarly for like you could use multi-layer perceptron as kind of your like prediction on the features and all these different things. By and large, I would say that you wouldn't expect to see much of a variation for the end model that you're training. What matters more is the kind of latent representation that you're using for the k-nearest neighbor search, right?
Yeah,
so like this
yeah,
kind of determine like what is near one another and thus like where the decision boundary is like roughly going to be. And increasingly for that, I think models are getting better and better as far as picking up on these details, clustering concepts very well for even unseen things. I mean, this is what we see in self-supervised work and like kind of metric learning, distance learning, and stuff like that.
That's very valid point. So basically, the model it doesn't really matter what model it is. So if we use your technique in it's not subsampling, but choosing the optimal kind of training samples for the model, it doesn't really matter what model it is. Like with your technique, it's basically the accuracy or the outcome is going to be almost comparable if it's not the same, with much less time. Not and again, it's agnostic to the model. Okay, perfect. And can you go to the recall curve for actually the two experiments, the ImageNet and yes.
Yeah.
So help me to kind of understand the recall curve a bit. So the MLP outperforms most like the MLP outperforms the max entropy and the information density.
Yeah.
Okay. And is there a reason for that?
Well, so again, kind of going back to the three methods, looks like you're positive is like the one method that is like active search specific. It's kind of like a very obvious active search method, and the fact that it's like optimizing for the things that are like most likely to be positive based off of the model's prediction. So it's going to end up with kind of giving you more positive examples, but it's not necessarily going to be better for kind of predicting class accuracy or anything like that. So there's kind of a trade-off depending on what your use case is. Are you in an active search use case where you really just care about finding these positive examples, something like the integrity use case where we want to take down these things, or do you care more about building an accurate classifier, in which case you would care about like the active learning and do like max entropy or do like something like max entropy uncertainty sample.
Awesome. Okay, so the thing that I get out of this is if I'm looking more for active search where I'm trying to identify these positive samples by itself, then MLP will help me with that. It's the recall is quite higher than the other ones, but then for the precision or the accuracy of the classes, as you explained, the max entropy could outperform the MLP. But so, for example, in a recommender system, if you're talking about recall and precision, usually there's this hybrid combination, which is the F1 score. If did you try an F1 score with this kind of model or no?
Not for this specifically. Mainly because of just like the existing metrics for kind of like this domain, like active search as kind of like maybe somewhat of a separation is focused again just like purely on the number of positive examples. Hence we represent recall in this sense is just the number of positive examples, but divided by the total number of like positive examples that exist. So it's more natural to compare up against kind of like existing work in the active search area. Yeah.
Okay. So we have another point here. Soya is saying that he was trying to work on a research project based on active learning. Is there any relevant sources that can get him started in this domain, and what are the hot topics that he can start working on in the field of active learning, of course?
Yeah. Um, so like there's many kind of great resources for active learning. I think it's super important as kind of a research area going forward. I think kind of increasingly data is a huge bottleneck, and so and also
Mm.
like when you think about it, machine learning models are the thing that we've seen kind of over and over again in is that machines are better at machine learning than humans in a sense, right? Like deep
Yeah.
learning as far as creating features, better at creating features, neural architectures are, and it seems obvious to me that like data will also be a similar thing. But as far as getting started, Settles has a great survey paper of kind of active learning in general and kind of like the kind of historical look at like what the different methods are, what people are considering. Thinking about kind of problems that people face now in active learning, I think there's stuff to be done about kind of the computational efficiency of active learning, especially in
Hmm.
the setting of like these large kind of data sets and computationally complex models.
Hmm.
There's a lot of work on either doing like batch active learning and like things like that to reduce the amount of computation, the amount of selection batches that you have to do. And a part of this selecting things in batches, you end up with a problem that you can be very redundant and you can select many
Yeah.
different things that are basically the same. If it's all like you have duplicates of the same thing, it's
Hmm.
going to all be the same, and then it's not going to actually be that informative. So there's a lot of stuff around diversity, I would say, in active learning. And then I think kind of another interesting area for active learning is possibly identifying or selecting with other constraints in mind rather than purely improving classifier performance in the traditional sense of like empirical risk minimization.
Hmm.
I think there was some great work recently at ECCV looking at, I think it was called contextual diversity or active learning for contextual diversity, where in that setting, they're like trying to select things such that you're like, let's say you want to have a bicycle and be diverse uh, to like if the bike appeared in like a city or if it's on a fence and stuff like that, and using kind of special things there
Hmm.
and special methods to ensure you have like diversity across these kind of other attributes.
Okay.
But yeah, at a high level, I would say like all of these are like super interesting areas, whether it be computationally diversity based or kind of optimizing for other things. I think is really great.
And I see it being applicable in a lot of different industries as well. Like I know most of the experimentation has been done with search optimization or again a commander engine, but I think with this kind of technique it could aid a lot of different other fields. And just top of my mind, cybersecurity is one of the fields that suffer a lot from very, very sparse data sets, right? So if you can use such a technique, it can improve the model with much less computation
So
complexity. And yeah, okay. So since we're talking about computation power, like if you wanted to train basically ImageNet, you'll need again GPU, right? You will need GPU to kind of speed up the process. But given your technique, like, did you use again, like, what kind of computation power did you use to train the model?
so initially for training the feature extractor, you use like a GPU to do that.
Mm-hmm.
But because of the fact that like, let's say in the open ImageNet example where we're just using a pre-trained model, you don't necessarily need to have a GPU to train the model. You can like go download pre-trained rates or something like that. And then just do inference over your data set to embed it to get this kind of initial representation of it.
Mm-hmm.
That
Mm-hmm.
makes
Okay,
sense.
that kind of makes sense. So
Yeah.
basically, also saving a lot on the GPU cost, which is very
Yeah.
crucial. Okay.
And
Yeah.
one thing that's also important to point out here is that like this initial kind of creating the embeddings and creating the index is kind of like a one-time cost that you might do up front. But
Mm.
now kind of we use that same index for all of the different concepts that we're evaluating. And you can imagine holding this index or like these embeddings for a very long time to be able to learn kind of new concepts as they come in. So like, for example, let's say in the cybersecurity example, there's like always new attacks. You create the index kind of once or like infrequently, and then you can actually be able to like use this multiple times as you have like new concepts come in and new things that you want to be able to find.
Okay. That's actually very interesting. So you're saying that like that one-time cost can be used in multiple different testing, um, assuming that embedding function was valid or it was good from from the first time. Once it is good, you can use it in multiple different purposes.
Yeah, totally. And just the index piece
Awesome.
of it in general, right? Like K-nearest neighbors might already have like a Similarity search engine for other tasks that you can leverage to be able to do seals.
Yes. Okay. Perfect. So again, we're open for more questions from the audience. Up until then, um, given this, like I feel that active learning is starting to come up a bit more dominant and frequently. Um, but it's like again, till today, I like there's not a lot of active learning or active fish specifically papers that is out there. Um, what do you think is going to be the most outcome if there's more if there's more research interest in it? What do you think is the best thing about having more extra research in this field? What do you think the most advantage will be?
Yeah, so I would actually say that I think this is like one of the topic areas where there's a slight disconnect between academia and industry. And the
Mm-hmm.
fact that when you think about an academic kind of data set or a paper or things like that, most of the time the data set is given to you, right?
Yes.
Like you're just like downloading image that it's predefined and you just use that as your task and you're focusing purely on the model. But
Mm-hmm.
it's actually kind of the flip from what I've seen in industry,
Mm-hmm.
where the data set is not given to you for any task, and you need to create that before you can do any type of modeling. And
Sure.
the quality of the data that you create will have kind of a huge kind of impact on the overall performance of the model that you end up using. So I think that because there's this mismatch between academia and like industry, I think there's a huge opportunity to do a lot of things there. And just like in general, I think it's going to become increasingly common for people to care about these kind of rare concepts. I've seen kind of a bunch of different work. Like if you talk to like Tesla had a great video about how they basically created their own like active learning streaming system because everything in the real world is hard. Like even a simple thing like a stop sign detector is
Mm-hmm.
hard in the real world because you have so much variety. You have
Sure.
included stop signs, you have stop signs on walls, you have people holding stop signs. And like being able to handle those edge cases become really, really important, right? When you're thinking about like a safety critical application like autonomous vehicles. But uh, also kind of another thing that I think is not reflected in kind of academic data sets is the fact that like many concepts that you care about and are interested in and potentially want to classify fall in the kind of like long tails of the
Sure.
distribution. So being able to find those things that are at those long tails, which I think are going to become increasingly important for machine learning as we think about, in general, we've gotten really good at, I would say, like the 80% case of machine learning. And
Yeah.
now kind of like the key differentiators and the key problems are in that tail, right? So it's things like safety, dealing with those
Mm-hmm.
kind of like extra like nines after your decimal point so that you are really sure that you're like accurate in all settings, as well as also things like diversity and kind of inclusion and fairness, right? Like if you think about accents and like a smart speaker, let's say you have a smart speaker deployment, it's going to be collecting like the majority of that data. Let's say it's like in the US, like households, and it's a very standard US accent. But if you have a different accent or a different way of speaking, finding those examples to be able to like actually deal with that is like critically important.
This is actually a very, very, very nice perspective. Yeah, like you're absolutely right. With most of the academic data, it is tailored for you to be using it. It's not just so data. It's actually massaged for it to be fed to a model with the least amount of work. While if you
Yeah.
go to the industry, there's tons and billions of different samples of the same thing, right? With very much different um, features that identify that whatever sample it is. Yeah, absolutely right, and I can see this hopefully being applied in a lot of different pieces. So, okay, so given what you have been talking about, is there anything you wanna add or anything you wanna mention before we take a last shot at the audience questions? After that, we can call it. Yeah.
Yeah, no. Yeah, I think at a high level, that kind of last point is really, really critical, right? Of just like, I think the world and kind of the problems that we're facing are more and more focused on the long tail.
Mm.
Either you have like new things that the world is constantly changing and you're adapting to, so you want to be able to identify those things. Or it's just like, again, the safety critical, you want to have some like long tail kind of, or even in the case of like integrity, right? Like people are adversarially kind of like going against you. So like trying to find those edge cases and things of someone like trying to go through the simple case is like is really really critical. And I think
Hmm.
creating data sets and like the process of creating data sets is a huge bottleneck in practice that's like understudied from an academic perspective.
Yeah, absolutely right. Okay, so my last question will be actually about the embedding function. So
Mhm.
we have data, we have labels, we have positive labels, so we're trying to use nearest neighbors to get those, or we're trying to use nearest neighbor algorithms to be able to get the embedding for those items or points. Um, do you have any state like first time to use embedding function that you go to the first at the very first time and you try to see if it's acceptable or not? So basically, what's the baseline embedding function that you usually use?
Yeah, so I think it depends on a little bit on the domain and the problem that you're doing. Um, I think either you could use like standard transfer learning, like the kind of thing that we've done here in open images. Also, like if it's like a close domain, like you train on image data, then like, okay, you get some reasonable features. But let's say you're in somewhere like, I don't know, medicine or some other domain where the actual information is very different than the thing that you're trying to predict. Another super promising thing, of course, is self-supervised learning.
Hmm.
And in the kind of more updated version of the paper, we have some results on self-supervised learning, where again, SEALs ends up improving the performance and kind of being very similar to active learning. And in that setting, you really don't need anything to get like up and running. You can train some self-supervised model, basically have that as kind of like your nice index. And a lot of this self-supervised work is increasingly getting more and more competitive to fully supervised learning. And then you just
Hmm.
train a very simple kind of like readout classifier, concept classifier on top of those self-supervised embeddings. And this is kind of a generic recipe that you can use for almost any task.
Yeah, yeah, fully good. Okay, so I don't think the audience has any more questions. Um, Once again, thanks a lot, Cody, for your time. It was really really nice reading about your work, and again, if you have any future work, we'll be more than happy to um, present your work again and work with it. Thanks everyone for attending. It was a pleasure being a host with you. If you have any questions for Cody, his email is on the paper. Otherwise, thanks a lot for a great presentation, and hopefully see you again. Thank you.
Awesome. Thank you. Thank you, Omar. Thank you, everyone.
Thank you.